right, we're back. Let's talk about some limiting reactant today and a little bit of percent yield. So as we've been talking about stoichiometry, we've been trying to figure out essentially how many grams or how much volume or how much of anything we could make from something we put in. Well, this is going to tell us how much we can make when we have two reactants, because one of them is going to limit you. So if you think about a recipe, you don't always have enough ingredients to make the full thing. Okay, so example, if you want to make some chocolate chip cookies, your recipe calls for 2 sticks of butter, you walk on over to the refrigerator, and you only have one. Sad face, because that means you can't make as many cookies as you wanted to make. You can only make half of the recipe. Double sad face, because I like me some chocolate chip cookies. So the butter limits how much product you can make, and we call this the limiting reagent or the limiting reactant. So if you think back to the s'more lab, how you were given a plate of ingredients, you were limited to how many full s'mores you could make. If you really remember, you know that the graham crackers were your limiting reagent.
Release the hounds!
So basically, all this is saying is that you can only make the amount of product that you have ingredients for. If you don't have enough ingredients, you're not going to be able to make as much product. So the only way that we can know how much we can make is to do stoichiometry. And we're going to have to do it twice. Count it, 1, 2, twice. So the way that you do this is that you take both reactants that you have with the amounts to the same product using stoichiometry. And then you compare those amounts. The one that makes the least is going to be your limiting reactant. The other reactants are always in excess. They don't get used up. So it's always key to remember, you cannot make more of any product than what that limiting reactant lets you make. Things react, react, and react, but as soon as one runs out, you can't react anymore. You can't make any more product as soon as one of them is gone. That one is your limiting reactant. And it's also key to note that you can also find how much excess you have of those excess reactants. Once you figure out how much your limiting reactant will let you make, you could work backwards and figure out how much extra was left over. So let's try an example. So if we had 1 mole of N2 and we have 6 moles of H2, how much NH3 could we make? And I'm just going to take this to moles because we could compare the moles. We could take it to grams, we could take it to volume, but either way, we're still comparing what these will make. So if we take 1 mole of N2, the way to get from one thing to the other is by mole to mole. So according to our balanced equation, we have 1 mole of N2 for every 2 moles of NH3. So if we solve that, that will give us 2 moles of NH3 that we can make with our N2. If we try it with our H2, 3 moles of H2. Our balanced equation tells us that we can make, we have 6 moles, sorry. 6 moles of H2. Our balanced equation tells us that we can make 3 moles of H2 for every 2 moles of NH3. So if we do that math, 12 divided by 3, we can make 4 moles of NH3. Okay, so this one will allow us to make 2. This one will allow us to make 4. We know that our limiting reagent is going to be the one that makes the least. So we can actually make 2 moles because as soon as we've made 2 moles, our N2, which is our limiting reactant, is run out. We can't keep reacting to get to this 4. So 2 moles is all that we can make. That's as much reactant as we have for that product. Keep in mind, just because this number is bigger than that number, you can't automatically assume that that's going to be your limiting reactant. These ratios here from our balanced equation will be different every time. So if this had been 4 moles to 3 moles or something different, it could have been a different outcome. Okay, so you have to do stoichiometry. You can't just look at things and figure it out from the number. So let's try one more example that's a little bit harder. Okay, so if we have this reaction And we want to know how many grams of water we can make, how many grams of lithium we can make, and what our limiting reactant is. And we're going to assume that we have 10 grams of each of our reactants. So, in order to figure out our limiting reactant, remember that we have to take it to the same product. So we're going to do stoichiometry twice here and try and figure out how much water we can make. And we need to know how many grams of water. We're going to ignore this one right now and wait till we know what our limiting reactant is, because in order to compare, it has to be taken to the same product. So when we see a chemical reaction, the very first thing that we should do, balance it. So if we have 1 lithium here, 2 over here, we need a 2. We have we'll say that this is the same thing as HOH. So we have 2 hydroxides here. We have 1 hydroxide here, so we need a 2. We now have 4 hydrogens, or 2 hydrogens. We've already used our hydroxide, and 2 hydrogens here. We have 1 sulfate and 1 sulfate. So our 2 and our 2 balance this out. Okay, so now it's time for our stoich. If we start with 10 grams of our LiOH, we are trying to find how many grams of water. So grams to moles, moles to moles, moles to grams, according to our mole map. So 1 mole of LiOH, if we add that up, is going to be 23.9 grams. Grams canceled. If we do our moles to moles, moles of LiOH to moles of water, from our balanced equation, we have 2 moles of LiOH to 2 moles of water. Our moles of LiOH have canceled. And our last step, if we take our moles to grams, moles of H2O this time, grams, which is 18 grams of water, moles of water cancel out. And we find that our 10 grams of lithium hydroxide will allow us to make 7.5 grams of water. Okay, but because we have amounts for 2 reactants, we have to do it twice, because that sulfuric acid may not let us make that much. So if we take our 10 grams of H2SO4, and same pathway, we're going to go grams to moles, and moles to grams again. So H2SO4 to grams, and if we calculate that out from the periodic table, 2 hydrogens, 1 S, and 4 oxygens, it's 98.1 grams. Our grams cancel. Moles to moles now, moles of H2SO4 to moles of water, and according to our balanced equation, we have 1 mole of H2SO4 to 2 moles of water. And our last step, moles of water to grams of water, and multiply across the top, divide across the bottom, and we get 3.67. So we have enough lithium hydroxide to make 7.5 grams of water, but we only have enough sulfuric acid to make 3.67. So as soon as 3.67 grams of water is made, the reaction stops. We don't have any more reactants. So that is the amount that we can actually make, 3.67 grams of water. Now we know that H2SO4 is our limiting reactant because it limited how much water we could make. If it's our limiting reactant in one case, it's going to be our limiting reactant in the other case as well. So now to figure out how much lithium sulfate we can make, we can take our 10 grams of H2SO4, because we know that that is our limiting reactant, and now we can find how many grams of Li2SO4. So same way, 10 grams of H2SO4, 1 mole is H2SO4, of H2SO4 is 98.1 grams, and our mole-to-mole ratio, we have 1 mole of H2SO4 to 1 mole of Li2SO4. So 1 mole to 1 mole H2SO4 to 1 mole of Li2SO4. And our last step, moles to grams. If we calculate the molar mass from the periodic table, we would get 109.9 grams. Moles have canceled, grams have canceled. And if we multiply across the top, divide across the bottom, we end up with 11.2 grams of lithium sulfate. So we can make 3.67 grams of this, 11.2 grams of that, and sulfuric acid is our limiting reactant. So let's think about what happens then with that reaction. Let's put this into real life. Theoretically, when a teacher gives a test, all students should get a 100%. You've gone over all the material, but we all know that that really doesn't happen. So if we compare this to chemical reactions, they're the same thing. Theoretically, everything should react, and you should be able to make 100% of the product that your limiting reactant lets you make. But that doesn't really happen. If that happened in real life, people would be rich because all of these chemical factories that are making things would be getting everything out that they put in. But it doesn't really happen like that. So the efficiency of a chemical reaction is something that we call the percent yield. Obviously, you want a very high percent yield because otherwise a lot of things are getting wasted. But it doesn't always happen like that. So the way to calculate this efficiency, or this percent yield, is similar to any other percent that we've worked with. We take the part that we're looking at, divided by the whole thing. This time, the part that we're looking at is the actual amount that we make, and we divide it by the theoretical amount that we can make. Just like when you take and try and find a percent on a test, you take the grade or the points that you got, and you divide it by the grade that is possible. So, percent yield is equal to our actual yield. Actual yield comes from the actual experiment. Theoretical yield is how much we should have made, and this always comes from calculations or stoichiometry. So actual yield divided by theoretical yield times 100 will give you your percent yield, your efficiency of that chemical reaction. So let's try this. If we have calcium carbonate, this is also found in seashells and in chalk, it's decomposed in this reaction. And if we look at this reaction, we notice 1 calcium, 3 oxygens, 1 here, 2 here, 1 carbon, 1 carbon. It's already balanced for us. What would be the theoretical yield of calcium oxide if 24.8 grams of calcium carbonate is heated? Now, if we're looking for the theoretical yield, we know that the theoretical yield comes from stoic. So, we have 24.8 grams of calcium carbonate. Okay, we know we have this one. We are looking for that one. So, 1 mole of calcium carbonate is 100.1 grams. If you think back to that chalk lab, we've actually already found that molar mass. And 1 mole of calcium carbonate to 1 mole of calcium oxide comes from our balanced equation. And 1 mole of calcium oxide is 56.1 grams. If we calculate that out, theoretically, we should make 13.9 grams. So if we wanted to find the percent yield, if we actually got 9.7 grams in our experiment, we take our actual yield, divide it by our theoretical yield, divide that out, multiply it by 100, and we would end up with 69.8% yield. Not bad. All right, here is your pop quiz. I want you to try this on your own, bring it to class tomorrow, and we will go over it. I will check to make sure that you have it done. See you next time.